Yeah, so welcome once again in MICHELSON Interferometer. We have already explained the aspect of interference caused by division of amplitudes, where we have looked at thin films and how multiple reflection cause interference. And now the experimental part of that interference by division of amplitude can mainly be done through Michelson interferometers and many other types of interferometers that we have. But for this lecture, I just want us to focus on the Michelson interferometer, what it is about, and how interference are caused, and probably the applications under Michelson interferometer. So, in this interferometer, there are certain important optical components that are used. For example, we have two mirrors which are labeled M1 and M2, and these two mirrors have very high reflectivity. They have very high reflectivity, and then they can also be adjusted. They are fixed with some screw that you can adjust the distance. You can move them forward or backwards so that you study the pattern of interference, and maybe if you are measuring, for example, distances, you can do that very accurately because those mirrors are fitted with that kind of measurements. Then it also requires the application of glass plates. These glass plates are, there are two of them. There is one that is painted with silvery, so that it can perform partial transmittance and reflectance. And we have one that is not painted, but they're identical. The two of them are identical, so yeah, they have the same refractive index and so on. Only that one has can transmit and can also reflect. So the setup in terms of diagram, let me show you. Yeah, so this is the setup where you have a source of light on one side. You have two mirrors. You have M1 and M2, which appears perpendicular. You have glass plates, P1 and P2, which are of course parallel, as you can see. And then you have glass P1, which is partially silvered. All right, so P1 is the one that is partially silvered, and it can also, so that it can perform transmission, it can do partial transmission and partial reflection. Then we have, of course, the two mirrors are adjustable and they are of very high quality. One thing to also note here is that if you consider ray coming from the source S, it first of all meets the first glass plate P1. It is transmitted, goes to the bottom surface, it is reflected, goes back to mirror M2, comes back to the glass plate, transmitted, and then goes to the eye. So if you count the number of times this ray passes through P1, you realize it passes through P1 3 times. The first time on the top surface, it is transmitted, goes to the bottom surface, reflected, that is second time, goes to the mirror M2, comes back to the glass, transmitted, that is the third time, and then it falls onto the eye. Then the second ray comes to the top surface of P1, it is transmitted, transmitted, and it is transmitted twice, transmitted through the glass and then transmitted to the air on the other side. And then it passes through glass plate P2 one time, goes to the mirror M2, mirror M1 comes back, passes through the glass P2, then comes through P1 on the partially silvered surface, and then to the eye. But what is important here? First of all, allow me to point out one difference. We take a scenario where we do not have the glass plate P2. Let's remove P2 from the diagram so that we have the first ray coming the glass plate. Sorry about that. Coming to the glass plate P1, transmitted one time, second time, third time, and then to the eye. While the second one comes to the glass plate P1, one time, goes to the mirror and back. So when you look at the two rays that are falling on the eye, it shows that one ray passes through glass P1 3 times. All right, one ray passes through glass P1 3 times, and the other one passes through the glass P1 only one time, the one that is transmitted twice. So to make the optical path difference the same, the glass P2 is inserted or is added so that the two rays will pass through the glass 3 times. Remember, the one that is transmitted second time will now pass through glass P1 one time, and then in glass P2 2 times. That will make it 3 times in total. So when you have the path difference within the glass being equal, then it means it is now possible to study interference. Remember, while we were looking at the interference caused by diffusion of wavefronts, we looked at a scenario where when a glass plate is introduced, it causes the fringes to shift. Fringes are able to shift by a certain amount depending on the refractive index of the glass. That is why for us to study the interference fringes, it is important that the optical path within the glass for the two rays is the same. And that is the reason why the glass P2 is introduced. And also remember, P2 does not have a reflecting surface. P2 does not have a reflecting surface. So that is basically what has been explained. And the other aspect to note here is that usually the compensating plate has to be used with a white light. All right, the compensating plate has to be used with a white light, or a laser light would work best with that compensating plate. So this movement of rays, we have already explained all that, why the second glass P2 is introduced, and that is to make sure that the light that is falling on the eye will travel through the glass material in equal distances, 3 times within the glass material. So then, how are fringes formed? How are fringes formed? Fringes are formed when you have the image of mirror 1 the image of mirror 1 appearing the apparent image of mirror 1 appearing slightly in front of mirror M2 or behind mirror M2 in such a way that the distance or the air gap between M1 apparent image of M1 and M2 will now produce interference. The same way, the concept of interference, thin films, interference caused by thin films, is the same way we look at the image of mirror M1 and mirror M2. That difference is what will produce interference. So the apparent position of the image of mirror M1 can be adjusted. It can be adjusted, and when that happens, it means the position of the fringes can also shift the same way. So in the so there's a little interference, but not light interference, but just physical interference here, but it's okay. So I was saying that interference here is caused by the air gap between the mirror M2 and M1, and so that the image of M2, the position can be adjusted behind M2 or in front of M2 to get different types of interference fringes. So when mirrors M1 and M2 are perfectly perpendicular to each other, the bounding surfaces of the image of M1 and M2 of the air film will be exactly parallel, and the thickness of that film will be equal to the difference between lengths L1 and L2. So I think also let's have this in mind. The distance, what is this L1 and L2? I'm going to go to the diagram. So L1 is the distance measured from the top of glass plate P1 and mirror M2, and the distance L2 is the distance measured from the silvered surface of glass plate P1 and mirror M1. So if these two mirrors are perfectly perpendicular, then the gap between M2 and the apparent position at M2 will be equal to the distance L2 minus L1. So that is what is being explained in this slide here, so that the distance D can have several values. It can be made to be equal to 0. That means it can be made to perfectly coincide with the position of M2. It can be shifted by a distance of equal to a quarter lambda, half lambda, 3/4, and so on and so forth. And this adjustment of the distance D is obtained by the screw that we had talked about, where these two perfectly reflecting mirrors are fitted with a screw, and the screw can adjust the position of the mirrors. So the distance D here is what I wanted to point out, that it depends on the distance of the mirror M1, and it can be adjusted to form different types of fringes. For example, if the mirrors are perpendicular, we expect to have circular fringes, and of course, if they are not perfectly perpendicular, we can get fringes that are not circular in nature. So then, if these mirrors are not perfectly perpendicular, then there is an introduction of an angle theta, which is now the deviation. The angle theta is what shows that, for example, if the difference is 89 and not 90, then theta becomes 1 degree, and therefore that angular difference is factored in terms of the path difference 2d, so that we only have now 2d cosine of theta. Remember, if they are perfectly perpendicular such that theta equals to 0, you will only have 2d equals to m lambda, where m of course is the order, and it goes back to, when theta is 0, it means the mirrors are perfectly perpendicular, and the fringes that are obtained are circular in nature. So this is just what happens when the mirrors are not perpendicular, a small deviation. So then, like we mentioned, mirror, the apparent position of mirror M1 can appear below M2 or above M2 in different points, or it can as well perfectly coincide with the position of M2. So these are different fringes that are formed for different positions of the apparent image. For instance, you see the fringe formed that is dark in the center is when the position of the apparent, the apparent position of mirror M1 appears to be perfectly aligned with the position of M2, so that the distance D is 0. Okay, so when the distance D is 0, the fringe formed on the screen or on a photographic plate appears dark. Now, when it's appearing below, you have the fringes on the left, as you see. So these two fringes on the left simply depends on by how much distance has it been moved below the mirror M2. The two fringes on the right simply shows by how much has it been moved above. So this is just what happens when you move mirrors, so that the apparent image appears after mirror M2 or simply below mirror M2 and so on. And also we note that when the mirrors are not perfectly aligned at 90 degrees, then instead of having a film of air that has equal thickness, you have one side tilted more than the other, and therefore the fringes are going to be produced by a wedge shaped film of air instead of a parallel film of air, and therefore the nature of interference will also depend on the shape of the wedge. That is also another type of interference, which is called the air wedge. Um, I mean, setting for interference, which is still interference by division of amplitude. But we didn't look at the air wedge interference, but I will encourage you to also read about it. Maybe I can get you some work so that you can read around that work to understand that type of interference more. Or I'm sure some of you must have done it in some other units. So the interferometer can be adjusted through the screws for the mirror M1. So we have already mentioned most of the things that are contained in this slide, that there are fitted screws on the mirrors that can be moved so that you alter the distance D1, and the movement of that or the adjustment of that distance is very important in the application, depending on what kind of application is intended for the Michelson interferometer. And of course, the adjustments also the idea of the path difference comes in, and that determines the nature of the images. So there are three main applications of the Michelson interferometer, and that includes measurement of wavelength of light, the width of fine structure of spectral lines, we have the measurement of refractive indices, and so on. So very briefly, I'm going to highlight these three applications. Like for the first one there, we have applications for measurement or determination of wavelength of light. So we have this formula already, where theta is the inclination angle or the deviation, and of course n is the order. So when theta is 0, you have the equation reducing to 2d is equal to n lambda, and therefore the distance d is what determines, the distance d is what is adjustable. You can adjust it in different lengths, and so if we denote the movement of the mirror by x, then we can say that the displacement x of M2 is equal to P, which is the number of fringes, that shift, when that adjustment is made, multiplied by lambda over 2. So this basically means that you can have whatever kind of displacement that is not necessarily a multiple of lambda and so on. And so because of that, you can have wavelength is equals to 2 times the distance moved, or just the displacement distance of the mirrors, divided by P, which is the number of fringes that cross a particular line on a cross wire. That is if you are observing it on a microscope or something like that. So that is just a simple explanation of how wavelength can be determined. Number 2, you can also determine the fine structure of spectral lines. For example, when you have a sodium doublet that produces two wavelengths, lambda 1 and lambda 2, it is possible to obtain like the separation between those two wavelengths of light using the setup of MICHELSON interferometer, and the equations here are described until you have lambda 1 minus lambda 2 equal to lambda squared to x, and so on. So again, much of it is contained in this literature here, and the equations are also easy to follow, where x is the distance of movement of one of either of the mirrors. And then finally, we can also determine the issue of the refractive index of a thin film. And the concept here is that when a glass is introduced in the path of one of the interfering rays, then you have fringes will be shifted, just the same way we did for the other interference under Young's modulus. So in this case, the procedure is that first of all, you don't insert the glass whose refractive index is to be determined, and then you have a cross wire. So you note the position of the cross wire, and then you introduce the glass that you want to determine the refractive index. Then you force that the fringes will shift, or the particular fringe will shift to a different location. Then when that happens, you make adjustments. You now make adjustment on the mirrors until the fringe is made to coincide back to the cross wire when it was noted before the glass plate was introduced. So when that adjustment is made, it is possible to get the number of fringes that cross a particular line, and that is equal to P. And so with that kind of procedure, you are able to get the refractive index of that material. So MICHELSON interferometer can also be used to determine the refractive index of a different type of material on the fact that a different material introduced on the path of any ray that is interfering will cause fringes to shift. And that shifting can be made into some good use, which is just to determine the numerical value of the refractive index of a particular material. So thank you very much. That was a very short lecture on the MICHELSON interferometer and also on the equations that govern the experiments of the MICHELSON. So I hope you will continue to do your reading so that you can enhance at least your capacity for interference. I will also get you more questions so that you can widen your scope to read other types of interferometers, and you can also make good distinctions between different types of interferometers. In your research, of course, in the lab, depending on the setup or depending on the nature of research that you're doing, you can perhaps need to use a particular type of interferometer. And so it is not good to only limit yourself to what we have discussed. Of course, this is just an eye-opener to give you some general concept, but you can also or widen the scope. So I'll prepare questions for you on other types of interferometers so that as you read more, you also expand your scopes. Otherwise, thank you very much for staying through until the end of this lecture, and see you in physical lecture next. Thank you. Bye.